In this lesson, we'll look at the architecture of MCUs. This lesson is an overview, and in later lessons, we'll go through some of this material in more detail. Now, here's the list of topics in this lesson. It's a long list. There is a lot of information. I've tried to squeeze it down, but there's just a lot to cover. And I think it's best to do the architecture overview in a single lesson. Rather than read through this list, let's just get started. First, let's look at some pictures. Here we see the naked MCU part. And above this, we see the package name for this part. These package names are industry standards, and you can look them up if you'd like. The digits at the end of the package name tell you how many pins it has. So this part has 64 pins with 16 pins on each of the 4 edges. Next, we see the MCU mounted on an STM32 Nucleo board, like the one we are using for this course. I want to point out that the Nucleo board is really 2 boards. There is a separate ST-Link interface part, I'll call this a subboard, that is attached by tabs to the main board. This ST-Link subboard is there only for debugging the main board. We'll talk more about this, including ST-Link, in later lessons. Finally, we see that this MCU, like many others, has different package options. The packages have different mounting schemes, in other words, how they are attached to the board with solder. They also have different numbers of pins and different physical sizes. Finally, some packages might have different amounts of internal resources, such as the number of timers. We can see that the number of pins ranges from 48 to 100, and the physical size ranges from about 3 millimeters on a side up to 14 millimeters on a side. Which package you would choose would depend on how much space you have on the board, the type of mounting scheme you want to use, which might be a manufacturing issue, and how many pins and internal resources you need. I'll be talking shortly about the pin counts. So here is a conceptual diagram of an MCU showing the stuff inside it. It is meant to represent many MCUs in use today, including the one we're using for this course. I created this diagram to cover most of the main parts, but not everything, and to emphasize the things we'll be working with on this course. As noted at the top, an MCU is an example of a system on a chip. The idea of a system on a chip is to take things that were traditionally in separate parts or chips and put them together on a single part or chip. This is beneficial because it makes the system smaller, cheaper, and generally use less power. On the other hand, it is sometimes difficult to add more resources like memory if you use a system on a chip. The solution is that the manufacturers offer a lot of MCU choices with different amounts of memory, and it is your job to choose an MCU model that has everything you need. Now, when I started in embedded many years ago, systems on a chip did not exist. All these parts you see here were separate parts on the board. Now, if you've studied computer architecture, some of this diagram should look familiar. So some of this lesson should be a review. However, there are things that are unique to a system on a chip that might be new to you, such as this pin multiplexer. So let's get started. I'll go through the diagram in groups where each group is a different color. Starting with the green boxes at the top, we find the heart of any computer system. A CPU to execute the software, and memory to hold the software and data. In this case, we have flash memory, which is mainly used to hold the software in the form of machine instructions. But flash can also be used for some kinds of data, as I'll mention in a minute. Why they call this flash is a little obscure, but it relates to how flash memory is very quickly erased, like the flash of a camera. Now, flash memory is persistent, meaning if power is removed, the contents are not lost. Obviously, this is critical for the software. However, Flash is kind of slow, especially for writing, and Flash can wear out if written too many times. Now, the software really doesn't need to be updated that often, even on a development board. But data might change quite often, say every few seconds. So normally you only use Flash for data if that data has to be persistent and if the data doesn't change that often. An example would be product configuration settings. Next to the Flash, we see RAM, which is used for dynamic data. In contrast to Flash, RAM is fast and doesn't wear out. RAM is normally not persistent, but some MCUs support a battery backup option for some or all of the RAM, making it like persistent memory as long as the battery is good. Just to give you an idea of memory sizes for MCUs, the MCU we're using for this course has 512 kilobytes of flash and 96 kilobytes of RAM. That's nothing compared to a mobile or a laptop, but it can be plenty for what the MCU is doing. Now, what if the internal memory is not enough? For example, say even the MCU option with the most memory is not enough for your application. Well, you can add extra memory parts to your board and connect them to the MCU. Accessing this external memory is slower than internal memory, but might be good enough. Below the CPU and memory is a red box, which represents another key part of the MCU, the system bus. I call it a part, but it is mainly just interconnections between parts within the chip. I will refer to these interconnections informally as wires, although they aren't the normal kind of wire you would think of. You will notice that almost everything connects to the system bus. The system bus is used to transfer data between parts. For example, the CPU will constantly be using the bus to get software instructions out of Flash. It will also be reading data to and from RAM. The CPU will usually less frequently be accessing these other parts through the system bus. I think you can see how a computer bus is like a bus transportation system in a city, taking people from place to place. Now, there are many kinds of buses in computers, and this system bus is a parallel bus, meaning that multiple bits of data are transferred in parallel. This makes it very fast. The downside of a parallel bus is that it requires many wires, say 20 to 100 or more. Of course, this is an internal bus, so all those wires are inside the chip. On larger systems like a laptop, the bus is external, so that it can connect to the large amounts of external RAM, for example. I need to mention, this bus is very simplified. In reality, MCUs often contain several buses that are interconnected. This is because a single system bus could be a bottleneck. Now, for the most part, you don't have to think much about the bus. An exception is if you use DMA controllers, which we'll talk about later. You might notice that a bus is like a network. This is true, and there is a little overlap in the words bus and network. The difference is that buses are usually local, like within the same computer, while networks can be very large, even worldwide. Now let's move down to these blue boxes, which are known as peripherals or modules. Sometimes the term device is also used. In this course, I always refer to these hardware parts as peripherals to try to avoid confusion. The term peripheral means it performs a function that is outside of the CPU's main function, which is executing the software. So this could be almost anything. Of course, you can have peripherals outside of the MCU as well, but for now we'll focus on these internal ones. I only show 3 peripherals here, but there can be many others of different types, as indicated by this ... We'll talk about the types of peripherals in just a minute. Note that the peripherals all connect to the system bus on the top side, and they have I/O signals on the bottom side that connect to the pin multiplexer. It is possible for a peripheral to not have any I/O signals, but most do. I'm moving away from our architecture picture for just a bit to show you a fuller list of the types of peripherals. Now, you're not going to remember all of this, it's a long list, but I want to give you a sense of what these peripherals are and what they do. So, UART stands for Universal Asynchronous Receiver Transmitter. You'll notice that a lot of the names here are not very descriptive, but that's what we got. Anyhow, a UART is used to talk to other systems, normally with simple text. This includes talking to a person on a console, as we'll see. A UART is a serial interface, meaning bits are sent one at a time. This is in contrast to the very fast parallel system bus we just talked about. Now, we use two UARTs in this course. The first for our console, and the second one to talk to an external GPS module. In the MCU we are using, they actually have USARTs rather than UARTs. USART means it has an additional synchronous mode of operation. You can read the name here. Because synchronous mode is not commonly used, I'll focus on the asynchronous mode in the UART. Now, timers. In the MCU for this course, there is one special purpose timer called the system timer that is normally used to generate a system clock for the software. In our case, that clock has a 1 millisecond tick. Then there are the general purpose timers. They are basically counters that can do different things based on how you configure them. They can measure time, or count pulses on an input pin, or generate pulsed signals on an output pin. The way they work is a little tricky, and it takes some time to learn how to program them. GPIO, which stands for General Purpose I/O, is used to talk to any external hardware that uses discrete binary signals, on or off, such as LED outputs and switch inputs. People might not think of GPIO as a peripheral, but I include it because there are a lot of similarities. An ADC is an analog to digital converter, and it takes an analog signal like the output of a microphone and converts it to a digital or numeric value. I2C, sometimes pronounced I squared C, stands for Inter-Integrated Circuit and is used to talk to other integrated circuits or chips. I2C is a type of serial bus, like a UART. Examples of what you would talk to with I2C is external sensors and displays. SPI stands for Serial Peripheral Interface. It is yet another type of serial bus, and it's similar to I2C. An example of what you would talk to with SPI is external memory, like external flash. Finally, we have DMA, which stands for Direct Memory Access Controller. Now, that name is not very descriptive. I think of a DMA controller as an automated data mover. There are many tasks that involve copying of data within the MCU. An example is sending data out on an I2C or SPI bus. That requires copying data from RAM to the peripheral. Now, a DMA controller can be programmed to do this task automatically. Otherwise, the CPU would have to do that work itself. And that is the key. The DMA controller is like a little helper for the CPU that gives the CPU more time to do more complex tasks. A DMA controller is one case where you might need to understand the system bus structure of the MCU. The system bus is designed with DMA controllers in mind to maximize the performance. So in case it isn't clear, I should point out that an MCU can have multiple copies of these types of peripherals. For example, the MCU we are using for this course has 3 UARTs and has multiple copies of some of these other peripherals. Now back to our architecture diagram. Let's move down to the pin multiplexer and electrical config. This is something I want to emphasize since we'll be working with this in an upcoming lesson. So you'll see that below these peripherals are some I/O signals. Different peripherals have different types and numbers of these I/O signals. Most times, if you're using a peripheral, some or all of these I/O signals need to get to the outside world. You get I/O signals to the outside world using these I/O port pins down here. These are the physical pins on the MCU. The pin multiplexer, which you might call a pin mapper, is used to connect a particular I/O signal to a particular pin. The problem is this. In many cases, an MCU has more peripheral I/O signals than there are pins. So you can't practically use all the peripherals at the same time. And no one really would expect to do this. You always have unused peripherals. And the problem becomes a little bit more complicated. The pin multiplexer is not super flexible. You can't just assign any I/O signal to any pin. Instead, for every I/O signal, there is a few pins that you can assign to it. Another way of looking at it, for every pin can be assigned to a limited number of peripheral I/O signals. In a later lesson, we'll look at a table that shows which assignments are possible. Anyhow, this can make pin assignment a little tricky. You have to select a set of peripherals where all of the needed I/O signals can be assigned to pins without conflict. But the IDE we'll be using knows about the allowed mappings, given it knows about the chip, so the IDE can help you choose peripherals and pin mappings. And one exception to the rule of limited flexibility is with GPIO. Every pin can be configured to be a GPIO. In other words, you never have a conflict trying to make a pin a GPIO. So to review, when selecting an MCU, you would have to decide which peripherals you need and verify that you'll be able to assign all the needed peripheral I/O signals to pins. Depending on your needs, you might need to choose an MCU package with more pins. This is because having more pins gives you more flexibility with pin assignments. As we'll see, the MCU used for this course has between 48 and 100 pins, depending on the package. The next box down is the pin electrical config. I show this as a separate box from the pin multiplexer, but they are related functions and you might view these two boxes as a single function. What this box does is control electrical characteristics of the pin. As a simple and obvious example, we have to know whether the pin is an input or an output. Another example, for those of you a little familiar with electronics, is whether a pin should have a pull-up resistor or a pull-down resistor, or neither. So now let's look at the interrupt controller. As you may know, an interrupt is a scheme to get the CPU to respond quickly to some event. Now a CPU has one or more hardware input signals to interrupt it. ARM CPUs generally have 2 such input signals, but in this diagram I just show one right here for simplicity. When an interrupt signal goes active, the CPU stops what it is doing and starts running code for the interrupt. This code is called an interrupt handler. When the handler is done, the CPU goes back to what it was doing. So what causes interrupts? Well, the CPU can internally generate interrupts, but for now we're interested in interrupts outside of the CPU. These typically come from a peripheral or a GPIO pin. For example, when the UART receives a character, it can raise an interrupt so the CPU can process the character just received. Now, as I mentioned, CPUs often have only a few interrupt inputs, maybe just one, but there might be many interrupt sources, say 50. This is where the interrupt controller comes into play. The interrupt controller provides lots of inputs for interrupts, say 50 or more. These inputs come from various places inside the MCU, such as the peripherals. When one of these inputs goes active, the interrupt controller will then interrupt the CPU. There is a hardware scheme for the interrupt controller to tell the CPU which interrupt happened in a very quick and efficient way. This allows the CPU to immediately go to the code for that interrupt source. For example, say the CPU found out that the UART caused the interrupt. It will then immediately run the UART interrupt handler code. You'll notice that the interrupt controller is on the internal system bus. This allows the CPU to configure the interrupt controller. For example, it can assign priorities to different interrupt sources and can disable and enable interrupt sources. We are nearing the end of this lesson. Just a few more things to look at. Let's move to clocks. Digital hardware usually works in steps, one step after another. For example, CPUs and buses work in a strict step-by-step manner. A clock is a signal that controls the steps, particularly how fast the steps run. Not all hardware works at the same speeds, so we often need multiple clock signals running at different speeds or frequencies. And there are ways in hardware to generate clock signals and to create faster clock signals from slower ones or do the reverse. And that's what goes on inside this clock generation box. Here you see clock signals coming out from this box going in all directions. This is to show that there are a number of clock signals, probably at different frequencies, and they are used throughout the MCU. The clock generation box is connected to the internal system bus to allow the MCU to configure the different clocks. Now, the IDE used in this course can help us by generating the clock setup code, and we'll be using that. Now, notice this crystal in this dashed box. Crystals are a way to get a more accurate clock. By accurate, I mean if you want a 1 second timer, you get a timer that is very, very close to 1 second. The better the crystal, the more accurate it will be. Crystals can't be easily miniaturized and put inside the chip, so an external one is needed. Now, MCUs often have an option of using an internal timing source or an external crystal-based timing source. The internal timing sources are not as accurate, but might be good enough for your product. Now, some final notes about clocks. Generally, the lower the clock frequency, the less power is consumed. It is not quite that simple, but that is a general rule. So there is a trade-off between power and frequency. Related to this, for unused or idle hardware, we often will turn off the clock entirely to save power. And finally, there's another kind of clock completely unrelated to these we've been talking about. It is called the real-time clock, or RTC. It is used to keep track of the conventional date and time of day in hours, minutes, and seconds. Accuracy is often very important, and sometimes there is a battery backup option so that the clock keeps running when power is lost. The last thing to look at is the debug interface. Now, this interface is your friend. It will make developing and debugging code much easier. We will be using it in this course. Using the debug interface, you can control the MCU via a debugger application, like the IDE, that normally runs on a laptop. You can also read and write memory. The debug interface also allows you to write your software into flash memory. Obviously, this is important. Now, note that these pins are labeled JTAG/SWD. JTAG is an industry standard debug interface. SWD, which stands for Serial Wire Debug, is an alternative to JTAG that was developed by ARM and is used for STM32 MCUs and perhaps others. The advantage of SWD over JTAG is that it uses fewer signals. I believe that SWD uses 2 signals and JTAG uses 5 signals. There are other debug interfaces as well, such as SWIM, Single Wire Interface Module, that is used for other types of MCUs. There are historical reasons why we have these different interfaces, but other than causing some confusion and creating extra work for some companies, they all do the same thing. Now, the arrows at the top of this box simply indicate that the debug module somehow interfaces to the MCU internally to support the debugging. There is some documentation that goes into this a little, but you don't really need to know about this unless you are developing your own debugger. Finally, I want to point out that this figure is a little misleading. It implies that these pins are dedicated to the debug function. In fact, these pins can be used for other purposes, and they really should be shown as going through this pin multiplexer. However, on power up, these pins are connected to the debug module by default. And that's necessary in case you want to take debug control of the MCU immediately on power up. So there you have it. If you made it to this point, your head might be spinning, but hopefully you learned a few things. I want to talk about one last thing. I mentioned a few times that these hardware parts are connected to the system bus so the CPU can configure them. So how does this happen? Well, as often the case with bare metal programming, nothing much happens without you. Software needs to be written that configures all this hardware, and that falls on you. Now, if you're using an IDE, then the IDE might be able to help out by generating some of this code, but ultimately the code is your responsibility. If there is a problem with the code, people will come to you. They won't come to the IDE. So anyhow, after the MCU gets power, the CPU will start running your code from flash, and one of the first things that your code should do is write configuration data into these various parts to get everything set up and ready to go. You will see how this works, including looking at the code in upcoming lessons. So that's it for the architecture, and thanks for watching.